Alright, this is the recorded notes for AP1 Physics for motion in a vertical circle. Alright, as we click here, we're going to consider the forces on a ball that's now attached to a string as it moves in a vertical loop. Note also that the positive direction is always going to be along the acceleration, and the acceleration is always towards the center of the circle since there is centripetal force. Remember, centripetal force and acceleration are always in the same direction. So, as I start with my ball at the bottom of my vertical circle, as I click through here, note changes to show the new positions. So, I have my free body diagram here as well as my velocity. So I have tension going towards the center on the string. I have my weight going down. So this is the maximum tension because tension is going to end up having to equal my centripetal force, and it's going to have to work grab against the weight force at this position. Now as I turn to the side, tension is now at a right angle to the weight, so it has no effect on, or weight is not going to have any effect on the tension. And tension is still equal to my centripetal force. Now as we start to move up around the circle, the weight is going to cause a small decrease in the tension because now it's going to be a portion of the centripetal force. Now at the top of the path, the tension is at a minimum because weight is going to be helping out the centripetal force. And so at this point, weight and tension are all going to the center, and they are helping with they combined create the centripetal force. So tension is getting some help from weight at this point. Again, on this side, weight has no effect on tension since it is at a right angle. So at the bottom again, as an exercise, let's talk about that the central force or the centripetal force is going to be 40 newtons. So we're always going to have 40 newtons going to the center, and that's really going to be our net force to maintain circular motion. And the weight of this ball is going to be 10 newtons. So the tension must adjust as we go around to always create that resultant or net force of 40 newtons going to the center. So if we start at the top, we have the weight force plus the tension force all going towards the center, and that has to equal 40 newtons. So tension at this point, we would be able to subtract the weight force from the central force or the centripetal force and get 30 newtons. Now at the bottom, on the other hand, it's going to be that tension is pointing upwards towards the center, so it's going the same way as the centripetal force, minus the weight force, which is going to be going down, and that will have to equal 40 newtons because that's the centripetal force. So we would end up finding out that tension at the bottom is 50 newtons. So at the bottom, it's going to be a higher tension value than at the top. So as we're continuing talking about the vertical circle, the resultant force is always going to be towards the center, and that force towards the center is going to be your centripetal force. So we're going to be able to say that mv squared over r is our centripetal force. Well, at the top, we're going to have our tension plus our weight that all have to equal our centripetal force. So if that's the case, I have mass times gravity plus my tension all has to equal my mv squared over r. So if I want to find tension, I could rearrange that formula, and it would be my centripetal force minus my weight force. When I'm talking about the mass being at the bottom instead, I have my centripetal force still being mv squared over r, and at the bottom, my tension is going the same direction as my centripetal force, and my weight is going the opposite direction. If that's the case, then we have T minus mg equals mv squared over r. So if I wanted to find the tension at the bottom, I would then say my centripetal force plus my weight force. So when we think about this sensation as we ride a loop-de-loop ride, so that we actually go upside down at the top, we need to think about the fact of where the forces are the greatest and where they are the least. Well, when we think about that, we can think about the normal force being just like our tension force. And that normal force is what we're going to feel as something pushing on us. So when we feel that, we're actually going to feel like we're the greatest at the bottom, according to my previous example, and we'll feel the least at the top because a weight is going to end up actually helping the normal force at the top. So if I look at it as free body diagrams, we can see how gravity and the normal force are both combined to at the top of the loop here at the bottom corner, and so my normal force is a lot less. So I'm going to feel lighter at the top than if I'm at the bottom of it, where that normal force is very large to create that net force. So to overtake the gravity. So it's the same as our chord, where instead we're going to talk about N being our normal force of the force on the track pushing up on the car. And then, so that's going to replace the T for our things. So at the top, we have our normal force pointing down, because it's from the wheels of the track, or the wheels on the track, or the track and the wheels together. So it's going to be pushing on the wheels towards the center, and then we have weight going towards the center, or straight down. So to find our normal force, we would say the centripetal force minus our weight force. Then at the bottom, we would do our centripetal force added to our weight force, since our normal force is going the same direction as our centripetal force. So it's exactly the same as we were talking about with the tension in the string. Now a Ferris wheel is a little bit different in the fact that the normal force is actually pushing up on you. So the normal force is actually pushing here, whereas the centripetal force and the weight force are going, centripetal force is going to the center, and weight force is going down. So we have our normal force and we have our weight force. Now something you do need to realize is centripetal force is a net force. And since it is a net force, it is something that you don't draw on a free body diagram. Okay? So N is in the direction opposite to the centripetal force at the top of the circle. So we would have mg minus N equaling our centripetal force, because mg is in the same direction as our centripetal force. So it would be positive. So if we were looking for our normal force at the top, we would have our weight force minus our centripetal force for a Ferris wheel. Now this is different than what we just looked at for the string, so just be aware of that. Now at the bottom, the normal force is pointing in the positive direction as the centripetal force, and the weight force is pushing, is still going straight down. So at the bottom, the normal force would be the centripetal force added to the weight force. So you feel a little bit differently on a Ferris wheel than you do on a loop-de-loop. So for motion in a circle, just in a review, if it's on a string, at the top, tension is the centripetal force minus the weight force. At the bottom, for on a string or a loop-de-loop, the tension is the centripetal force added to the weight force. So the force on the ball is the least at the top, and the force on the ball is the greatest at the bottom. And that force that we're talking about on the ball is really the tension in the string. So for a Ferris wheel, though, our normal force at the top will be our weight force minus our centripetal force, and at the bottom it'll be our centripetal force plus our weight force. So summary, centripetal acceleration is v squared over r, which can be used in the formula of F equals ma, which would then become mass times velocity squared over r when we're talking about circles. Then, for our vertical circle, loop-de-loop, at the top, we have our T equals mv squared over r minus our weight force. At the bottom, we have T equals mv squared plus, or mv squared over r plus our weight force. And at the bottom, we have our normal force would equal, for a Ferris wheel, at the bottom we would have normal being our mv squared over r plus mg, remember I said at the bottom, and at the top we would have our normal force being our weight force minus our centripetal force. So the formulas just change according to where your forces are pointing. So just pay attention to where the forces are pointing, and remember that the positive is always towards the centripetal force, because the centripetal force is a net force. All right?